I will use this example to explain goodness of fit test. Goodness of fit test is used to check whether your observed data have certain distribution. Okay, so for example, in this example, in one of his pea breeding experiments, Mendel observed the following frequencies of seeds. So you can see, there are four different categories, right? So the first one is round and yellow, round yellow. So we have 315, and we have round and green, round green. We have 108. We have wrinkled and yellow. So we have 101, and we have wrinkled and green. Okay, and so the problem is we want to know whether the data fit 9 to 3 to 3 to 1 ratio. Oh yeah, so this is 32. Okay, so what we want to know is whether the probability will be, yeah, because 9 over 16, 3 over 16, 3 over 16, and 1 over 16. Yeah, you can see. So if we draw a line, basically the total, right? So see the sum of these four probability equal to 1, right? The sum is equal to 1. Okay. We can also calculate the sum of the frequency. Yeah, so basically 315 plus 108, 101 plus 32. So this total will be 556. Okay. So now we want to get a test statistic. So basically, the test statistic will have this form, the form summation of the observed minus expected, square, and over expected. So what is observed? Yeah, so this column is observed. Observed just means observed frequency. Yeah, so basically just the number from your data. And what is expected? Expected means the expected frequency under your assumption. Yeah, because in your assumption in the probability, right? Basically, you assume this four category has this probability, right? So the expected just will be the total times the corresponding probability. For example, for the first category will be the total. Total is the total frequency times the 9 over 16. Okay, so this is the expected frequency equal to 312.75. So this is the expected frequency under the null hypothesis. So for the second category, 555 times 3 over 16, you do the math, 104.25. Similarly, 556 times 3 over 16 equal to 104.25. So the last category, the total frequency times 1 over 16. So this is the assumed probability, right? And so equal to 34.75. Okay, so now we got observed frequency and we got expected frequency. Okay, so basically for each pair of them, and so then we will use this basically formula to calculate the statistic, right? So statistic x squared, and so it is equal to, see, observed for the first category, observed is 315, expected is 312.75 square and divided by 312.75. So 312 and 75, this is expected. So we do this for the first category, right? And so then we do the same thing for the remaining category and add them together. Yeah, so this is 108 minus 104.25 square over 104.25. And then plus 101 minus 104.25 square 104.25. And then plus 32 minus 34.75 square 34.75, right? Yeah, so this is the formula we use to calculate the statistic. And so if you do the math, so this is 0.47. And to get the p-value, okay, so p-value is always the probability, so the statistic greater than or equal to the test statistic we calculated. Yeah, so notice the degrees of freedom is C minus 1. So what is C? C is just the number of categories, right? So basically for this one, so C, we have 4 category, so 4 minus 1 equals to 3, right? So then when you calculate the p-value, yeah, so this p-value cannot be calculated by hand, and so using Excel, so this is 1 minus chi-sq dot dist and the statistic 0.47, degrees of freedom 3 and 2, right? Yeah. Okay, and so the p-value is 0.9254, and we compare the p-value with alpha. Alpha is 0.05, so p-value is much larger than alpha, and we fail to reject the null hypothesis. Yeah, so we will claim so the category so follows ratio 9 to 3 to 3 to 1.